who we are, Lucidian. So you've probably not heard of us, where our areas of expertise lie, and some of the challenges of testing programs that we come across. I'm going to go through a few examples and then look at some learnings that we have from that. So who we are, so Lucidian, we're a materials technology company. So we're working in the sort of materials development, materials testing, etc. We have a large R&D capability, and that's supported by a lot of testing capability, characterization. We're UK based in Stoke-on-Trent, but we've got capabilities in the US, both in North Carolina, South Carolina, and New York. We have a long history of working in regulated industries, so that's not just within the aerospace, but also within nuclear, within healthcare, and other similar industries. We've got a relatively small workforce, but highly specialised and highly qualified around that. And where we really sit is bridging that gap between academia and industry. And as I say, it's very much on the material side of it. So what we actually bring, where do we sit? So we're actually sitting in a sort of triangle between research and development, materials consulting, and specialised testing. And the more of those things that can interact, the better as far as we're concerned. So on the research and development side of it, we're looking particularly in myself at advanced ceramics. That's one of my areas of expertise. We're working in accelerated materials discovery. So this is new materials for new applications, and we've got some platform technologies around that. Beyond that, into sort of wider materials, we're looking at materials optioneering. We're looking at process support, particularly around additive manufacturing. We're looking at failures of systems and understanding those, and very much around harsh environments, how materials are used in those. There's certainly a big change in materials needs for aerospace at the moment, both with fuel issues, so carbon reduction, so making aerospace industry more fuel efficient. So how can things be operated at lighter weighted, higher temperatures, how things can go faster. All of these put challenges onto the materials that fundamentally are in there. So for instance, the sister meeting around London to Australia in 5 hours, you can't do that with conventional materials. You've got to change things quite dramatically. All of a sudden, the outside of, or certainly parts of your airframe, become not sort of normal, inverted commas, ambient temperatures, but very much hotter because of those hypersonic speeds. So you're actually moving technologies effectively from inside an engine onto the outside of that. So there's going to be some huge changes on those sorts of sides of it. On the testing side of it, we've got very specialised capability around surface science, so looking at the outermost layers of atoms on surfaces, understanding what's going on, and within the mechanical testing side of it, very much specialised capabilities around that, trying to match what we're doing. And then working in sort of environmental temperature extremes, so thermally, typically up to about 1500 where we can operate, and we've now also installed some cryogenic capability, but that's unfortunately on the wrong side, well, on the other side of the Atlantic, but in our organisation. So what we've got characterization-wise, we do a lot of taking things right back to the beginning. So we're actually looking at the chemical composition. So this is actually, what are the building blocks in those materials? Can we measure it? What's there? Is it compliant? What's the variation, etc., etc. So lots of capability from ceramics, metals, and polymers within there. you've then got to combine those. How do you put those different chemical entities together? So we're looking at the microstructure, what crystallographic, what physical structures are we making? How are those then actually pulled together? How are those made into structures? So we'll be looking at the microstructures, what's the grain size, what's the porosity, how do those bond together? Looking at fractography, looking at failures, how have they failed, and what's gone wrong? What can we learn from those? Surface side of it, we're looking at, as I said, very near surface, so the outermost layers of atoms and molecules. So if we think we've actually gone and cleaned something, we certainly haven't cleaned it. There is always residues on those. Understanding what those are and where they're from can be really quite important and enlightening. Similarly, also topography. A lot of things are actually topographic, even though they may appear to be contamination or discoloration. Then going into some of the other things, so a lot of capability around mechanical testing, as I say, so flexural, stress strain, etc., but also looking at the actual feedstock materials into those. What do they actually look like? Do they have the right properties, performance? So quite a wide range of capabilities. And then going on to sort of environmental exposure, how can we challenge those materials into environments that we're actually going to be seeing? So what can we do temperature-wise, what can we do age-wise, and what can we do thermal exposure-wise? And then obviously corrosion, again, is an area, and one particularly unique capability is stress corrosion cracking, where we're actually looking at long-term crack growth within systems on that. So when we actually come back to testing programs, there's a lot of unpicking of those quite often is actually needed. And fundamentally, to me, it always comes back to what the aim of what we're trying to achieve is. What are we trying to achieve from doing whatever piece of work, whether it's evaluating a material, whether it's evaluating a component. So it's kind of the why. So what conditions are we looking at in? Are we looking at doing it just on the bench at ambient, or are we actually looking at trying to replicate some sort of environmental conditions that it might be expected to see? Are there defined test criteria? What's actually needed within those requirements? Sometimes that's very clearly defined, other times it's much harder to do so. What are the materials themselves? Again, this has a big impact on how we'd actually go about evaluating it. Big move in in composites. So where you'd have had traditional polymeric-based composites, now you've got ceramic matrix composites. Again, how you test and evaluate those is very, very different. And then sometimes you'll be working standard methodologies with the changes within materials, conditions, requirement, and particularly if we're stretching where those environments might be, there might not be appropriate standard test methods. And I've just put out some numbers of just really within the sort of EN, ISOs and ASTMs of how many different test protocols there are out there. And these are just very simplistically looking at the pure numbers of tests that are on the table. And this is across spectrum of materials. So, and again, it's, well, which of those are then appropriate to what we're trying to do? So if we pull out that flexural strength measurement, again, some of those are within, and then we narrow it down to some of the material types that we might be interested in. And there, I've just looked purely at some of the non-metallics, and very quickly, those numbers collapse down into much fewer test methods. But again, are they appropriate for what we're trying to do? So within the test programs, there's always a lot of complexity, and certainly with materials, we're looking at making things lighter, making things operate higher temperatures? What other material options are out there? So how can we push that boundary forward? And within that, there's never going to be a straightforward way of testing that. So there's a lot of complexity. What material? How are we going to do it? Timeframes, we might have considerable constraints around timeframes of what we've got to do, and sparsity of material. If we're in a material development stage, we've almost certainly got much less material to work with than we would like to. Test parameters don't always work with the material that we're looking at. So yes, we might have a target of what we're trying to do, but actually, because of some constraint, we might not actually be able to get there. Test methods may be there, they may not. We might have to modify those in some ways. And clearly within that, there'll be a lot of conflicting priorities. So depending on how much material, you might have to do things sequentially. However, if timeframes are more important, then things like that fall by the wayside. So really, it's how do we map that out? So back to the purpose, what are the must-haves? What have we really got to get from what we're trying to do? We might have some peripheral nice-to-haves around that, but key within that is that sort of drop dead, we must have this. Understanding what's available material-wise, and what we've got to do to prepare and make those materials into specimens, how we're going to pre-treat, how we're going to equilibrate that. And then we've got a sequence of testing, so we may have to do we may be able to do some observational things first. We might have to pick the right test protocols, test methods. We might have to develop methods specifically for that particular application, and how many tests are actually valid for what we're trying to do. We could then go through, we get the required material, we collect the data, we collate that and pull that together, and all the way through we have to review it. So really we're trying to put together that program and then really unpick that. Have we covered all those bases within there that we need to? So finally, let's agree and finalize that work plan. So all perfect, everything going forward. Okay, so now we actually start doing it. And this is where things invariably never quite go according to plan. So initially, have we got all the documentation in place? Have we got those pieces of paper? Do we have traceability of material? We undertook a piece of work a couple of years back, and the tracking of those actual parts before they got to us, there was problems with that, which to a large extent then invalidates a lot of the work that you've done. So it's really trying to make sure everything's done to make certain that we're going in the right place. We got the material. Is it actually as we thought it was going to be, or is there something fundamentally different? Is it thicker? Is it thinner? Does it have holes in? There's quite often something that you never quite saw or anticipated within that. So always having a little look and see. Prepared the specimens again. Are they fit for purpose? Can we progress within that? We go through, we collect all the data that we need to, all the way through, keeping an eye on what do we see, what do we look at, what do we interpret from that, and similarly when we get data. So, as I say, there's always something happens that shouldn't, or something unexpected that happens. So, first question is, what are we going to do about it? So, does it compromise what we've seen? Does it compromise the data or the methodology? Does it invalidate what we're actually conducting? Or have we seen something that we didn't anticipate or expect? So essentially that's where we would get to. And there's really three scenarios around that. We either carry on, we go over the trenches and just battle on going forward. We react and learn and probe around that. What's that telling us about what we're looking at? What else can we find from that? Or actually, do we have to stop, stand back and regroup and replan. And quite often, particularly with materials that are novel or in applications that are, we do come across those sorts of scenarios. And then whatever we do, we've got to agree how we're going forward with ultimately whoever's paying the bill at the end of the day. And clearly keeping that onward flow is absolutely key. So I'm going to pull through a number of different examples of things. Some of them are around in ceramics, some of them are not. Clearly, as I say, my expertise is within the ceramic area. So one of the things that we actually work with is ceramic cores. And so ceramic cores are a sacrificial ceramic part that gets cast within a turbine blade. So if you make a turbine blade, what you would generally do is have cooling channels within these. So you would actually cast a ceramic component that goes in that is sacrificial. So the key thing for that is its shape. So got to have a uniform shape. It's got to expand uniformly. So it's got to expand. You can't have it stretch in one direction or twisting or warping. And it's got to be readily removed at the end of the day. So they're the sorts of things that you're trying to do with it. It's how do we actually accomplish some of those. So we'll pick one of those out. So thermal expansion. So that's how much it grows and shrinks. Now, we could make a bespoke test specimen with all the parts and goes through, but it's actually a different shape. It's formed differently. Is it actually a true representation of what's being made? Maybe there's time constraints in there, but actually that part has been specially designed with mineralogy that controls some of that thermal expansion. So rather than actually measuring that, what we might want to do is step back and measure an analogy of it. So, and trying to keep that going through. This is a ceramic matrix composite development that we've been working on. So this is quite a thin walled structure. So in this case, it's probably about 2 millimeters thick and capable of high temperatures. So in the sort of 8 to 1200 degrees. So not massively high, but not massively low. And what we were looking really is here, some indicative data. And really, we haven't got much parts. What data do we actually collect? So clearly the structure of the component is very important. So we want to understand how those fibers put together, how they're meshed together, how they're bonded. So we've got to collect that sort of data. We want to look at the thermal performance of it. What happens when you heat this up? And what you can see there is a whole sequence of different trials of modifications to the actual material itself. And you can see how we've changed a couple of the parameters. We can dramatically change its dimensional stability, its shrinkage, etc. So clearly within that, we've got sweet spots that we're actually working. So these are the sort of steps that we're getting through to try and get to where we want. And then we need to measure some mechanical properties. So in this case, we're doing some flexural strength measurements. And again, here we're looking at deformation, deflection of it. And again, how far that will be is quite key. So another piece of work where we're actually looking at some interfaces in a very novel application. And what we're trying to do is we're looking at a whole sequence of different options, and we want to make them fail fast. We want to get rid of things that are of no use to us with minimal effort. So we challenge it as severely as we possibly can early on. Unfortunately, in this case, we went too far and everything actually failed on it. So we've got to roll back from that. We've got to replan that in that our scenario was somewhat extreme. So redesign the test methodologies. We did, because we're looking at interfaces, we redesigned the way we're actually doing some of these lap shear type measurements, really to try and get much better data than we would have done otherwise. Another area that we do a lot of, and this is particularly my colleagues who are US based, is around AM processes, material characterization. So in essence, a lot of the things come back down to the feedstock materials, understanding what they are, and seeing what we come across within those. So we're looking at the feedstock materials, we're looking at those processes, and at each stage evaluating, unpicking it and seeing what's in there to learn, and then recycling the material. So in the vast majority of material in the 3D print is not used in the final part and goes back through that process. And it's how we actually recycle that, how we look at it, how we evaluate it, and how we validate that. So, as I say, all comes back to powders. So again, what can we learn from it? So here we've got a sequence of different preliminary powders. You can see little satellites on there. And what we're doing is evaluating different processes of modifying that material into a way where it can actually produce something that is consistent at the end of the day. And you can see there's quite a difference between the virgin powders and how they've been once they've been through that powder bed. And again, there's not just the outside of the material, you've got the inside, so you've got internal porosities within those, you've got shape structures, you've got little surfaces, some of them have been partially melted, remelted, they've got stuff melted onto the outside. So a lot of variability, and we need to understand those. Not all little satellites are satellites of what you'd expect. So in this case, we've got a titanium-based powder, and we've got contamination. And on the face of it, they just look like little satellites, cell particles. But when we start looking at the chemistry, we actually find that they are chemically very, very different. And in this case, we've got some fairly gross copper contamination. When we're making structures that are variable internally, we've got porosity in there, we end up with a lot of surface topography. You can see there a lot of metallic particles are semi-molten into that surface, and they do have a habit of shedding and falling off within that. And we've got to understand all that system. We've got to go through those destructive testing programs to see what's actually happening, and if need be, non-destructive, how do they look internally? This is as fabricated AM, as I say, and what we've got is we've got a titanium-based alloy. You can see the little bead structure, but if we look in detail at some of those chemistries, what we're actually picking out there is a very thin film of aluminium between those two particles. So what we've got is we've got a necked area that is a relatively weak material that's got a relatively low melting point, and okay, that bead as it sounds probably is completely irrelevant, but if that's endemic right through that system, we've got to really know about it. So very often we have to look in some considerable depth to really see what's going on. So really coming back to the learnings, we need to focus on what the purpose and what's important. What do we really have to get from this? We need to consider all the planning to make sure that we've got a logical sequence, and we've got to be very prepared to amend, curtail, and redefine that program as we go. Again, really coming back to what is the data for, what do we need to get out from it, and all the time we have to collect that information, observe it, what can we learn as we go from that material. So thank you for that, and if there are any questions. Over there.
Are you actually making those materials, or are you outsourcing them?
In that particular case, that is an oxide-based system that we are developing and making ourselves, and it's a route with a low temperature formation process. So rather than it being a high temperature formation, we're actually looking at a low temperature process to get to a temperature stable material.
Are you able to study this material at elevated temperature?
We're able to study it at elevated temperature, that's correct, yes.
And what about its EMC performance at elevated
We're
temperature?
not anywhere down that line yet, so long way to go.
Thank you.
Okay, thank you.